In the following video, you will hear excerpts from a media briefing given at ESA's European Space Operations Center in Darmstadt, Germany on December 10th, 2013.
But what we know today scientifically about comets is that they are time capsules. They are remnants of the birth of the solar system. And they age, they go back to the beginning of the solar system more than 4.6 billion years ago. And when the solar system was forming out of gas and dust, it formed the planets, the one we live on today, it formed asteroids, and it formed the comets. And the comets are a remnant, therefore something we can investigate about the very earliest phases of the evolution and the birth of our own solar system. And so unlocking these time capsules, looking at the gas that come off them, the dust, and in particular the ice, the water that they're made of, give us great clues to the origin, not only of our own solar system and the planets, but potentially even life. Because we know that comets also contain organic molecules, the building blocks of even DNA and RNA. We know there are amino acids in comets, for example. And so comets play a key role in our understanding of the cycle of star formation, planet formation, perhaps life formation, and the development of the people who are here today going back out to dig into a comet to find the origin of our world and perhaps even of life here on this planet. And of course, with that in mind, comets are therefore a Rosetta Stone, a way of translating between the evidence which lies in our solar system and the evidence we have on the Earth today, hence the name of the mission, the Rosetta mission. Now, we have a heritage here in the European Space Agency because, of course, in 1986, on a subsequent return of Comet Halley, ESA and various other international partners, including the Japanese and the Russians, decided to go to Halley. And we went with our satellite Giotto and conducted a successful flyby at Comet Halley in 1986. But we conducted a flyby. We flew past at 250,000 kilometers per hour, and we flew by at several thousand kilometers. And so we had fleeting images of this comet. Actually, sorry, do I have the number wrong? It's 600 kilometers. I need to correct myself. But still, 600 kilometers is a long way away from the comet. We needed to do that, though, because we're emerging. We're going to come into a region full of gas and dust, as you can see in the pictures in front of us here. And of course, we're traveling at such high speed, 250,000 kilometers an hour, there's a danger of collision. And in fact, Giotto was hit by dust as it passed by Halley, but not before it took these pictures. It later went on to another comet, Grigg-Skellerup, not with any imaging anymore because the camera was damaged. And we visited several comets over time in flybys, and this is another one. This is Hartley 2, seen by one of NASA's missions, EPOXY, in 2010. And there's a very interesting fact about Hartley 2, which is, again, what illustrates one of the scientific reasons why we're going to the comet with Rosetta. And that is, we believe that comets are mostly made of ice, although we don't know the proportion. There's a lot of dust, there's a lot of rock, there's a lot of particulate material, and there's also ice there and water there. But is that the same water that I have in front of me here? Is that the water I'm drinking today? We know that the great majority of the water on the Earth must have come long after the Earth was formed, because when the Earth was born, it was very hot, and there would have been no water on it. So that much of the water on the Earth must have been delivered later from somewhere else. And comets, perhaps, are an obvious source. But until very recently, with another of our missions, the Herschel Space Observatory, the evidence was not compelling in the favor of comets. And the reason is, if you look at this chart, and it's about the only scientific plot I'll show you, this is the isotopic ratio of water, the ratio of hydrogen to deuterium in water on the planet Earth. And you can see the Earth there is the blue line, okay? All comets measured prior to this measurement of Hartley 2 showed a higher ratio of deuterium, a higher amount of deuterium in comets than in the water on the Earth. And if the comets delivered the water to the Earth should reflect that. But it doesn't. Not at least until Hartley 2 was measured. And that's the purple square at the end there, as I've put an ellipse around here. And that tells us that, in fact, some comets in the solar system, and these are a special family of comets, the so-called Jupiter family comets, which live in the inner solar system, they were born further out, but migrated in towards the inner solar system later on. that Hartley 2, as a representative of that family, does have the right deuterium to hydrogen ratio. And so therefore, if there are many, many such Jupiter comets, Jupiter family comets, which have collided with the Earth, and we know that comets hit planets, then the Earth's water, this could have come from a comet. So cheers. After that. Well, we're going to go and do science, and we're going to do it on this object, 67P Churyumov-Gerasimenko, or to you, 67P CG, okay? This is a Jupiter family comet, which spends most of its life out around the orbit of Jupiter, but dips into the inner solar system between Earth and Mars. It doesn't go all the way in close to the sun like ISON did. It nevertheless gets warmed up and will evolve and will outgas and make jets and a coma. Okay. One of the problems with comets, though, if comets that live in the inner solar system, if they go around the sun, around and around and around, they get heavily processed. And in fact, the surfaces of comets are not icy at all. They're dark, they're black. They're blacker than road material, asphalt. Because all the volatiles on the surface have been driven off, what we're left with is tar, something like tar and muck on the surface. And so if you have a comet which has spent all of its life like this in the inner solar system, that's not necessarily the perfect comet. But 67P CG only moved into this close orbit in 1959. It had an interaction with the sun, with Jupiter in 1959, which moved its orbit in by several AU. So it actually spent most of its life further away from the sun and isn't as processed as many other comets. So you see all the numbers there, all the things we like to learn about in comets, and you can see at the very bottom there that its orbital period is 6.5 years. So every 6.5 years it comes around. And of course, that's in one of the ways why we can go to it, because we know where it is. We could never have gone to ISON. We couldn't have launched a spacecraft in time to intercept something moving so fast through the solar system. Now, we also know, over the last few years, we need to know something about how active the comet's going to be. Because if we're going to land on it, we're actually going to land on it quite far from the sun, because we don't want to land on it when it's at its most active. So astronomers have been looking at CG over the last few years and have worked out that actually it's going to be starting to get active in March next year already. So material should start flowing out from the comet. And that's before we get there. But we believe that it won't be so active by November that will be a problem for operations. But it adds this element of risk and excitement to the whole mission, that a comet is not just a static object, it's a volatile object. It's going to be changing the whole time we're there. And we also know from further analysis actually what the comet looks like in terms of its activity. We have a model of the comet, again based on the light variations. We believe that there are 3 active regions on this comet, and they've been active over several orbits. The same regions are active each time. As they turn into sunlight, warm up, material flows away. We see material then flowing into the coma. And so we already have an idea about the shape and the activity and where those jets might be. But again, we're going there to learn much more. And we're going there not just with the spacecraft, but of course with scientific instruments. And I'm not going to go through them all one by one, but these are all the instruments with all of their acronyms, which is another thing, another challenge you're all going to have to learn what they all do.
There's a film that shows what is going to happen on the 20th of January. It's only a couple of minutes. It's worthwhile going through it in detail. Also to explain why it takes so long to wake up. As I said, there is a timer on board which has been set for wake up at 10 o'clock UTC on the 20th of January, at a distance from the sun of 673 million kilometers. The spacecraft is spinning, keeping the solar rays more or less towards the direction of the sun. And when the timer expires, the first thing the spacecraft will do will switch on heaters and wake up the star trackers. You see these 2 red items there. They're important for determining the attitude. It will take 6 hours to warm up the star trackers, and then with thruster firing, the rotation will be stopped. We will direct, well, the spacecraft autonomously will direct the solar rays exactly pointing to the sun, and start a very slow rotation that will allow the star trackers to acquire a star field that they can recognize, and they can determine autonomously the actual 3-axis stabilization, 3-axis position attitude of the spacecraft. Once that has happened, the spacecraft can orient itself in the direction of the Earth. Once it knows in which attitude it is, it knows where the Earth is. Rotates and then points the high-gain antenna. We need the high-gain antenna because, of course, with this distance of 800 million kilometers, we need all the amplification of the signal that we can. This is a 2.2 meter antenna oriented towards the Earth. At this point, about 7 hours or 6.5 have passed from the wake-up. The signal starts to travel to Earth. And as I said before, although it travels at 300,000 kilometers per second, it will take 45 minutes to reach the Earth. That's towards the late afternoon of the 20th of January. That's the earliest time at which we expect the signal on ground. Of course, of all these automatic operations, there can be delays in there can be repetitions. So there is a large uncertainty, which is of the order of several hours on the actual timing of the expected signal. Once we do all these maneuvers and we get around the comet, we have to learn, as I said before, how it looks like. So first of all, that's what we're going to do, or what we plan to do. We arrive in August, and we stay at distances of the order of 100 kilometers, and we fly these what we call pyramid orbits. You are used to orbits in terms of circles or ellipses around an object, but you have to imagine that a comet is so small, it has hardly any gravity, it has a lot of disturbance torques due to the gas, to the even the radiation pressure of the sun is of the same order of the forces that are involved in this orbiting. So we can do, in principle, what we want. On the other hand as well, these orbits are very unstable, so we have to be extremely careful. So each side of this first pyramid is about 100 kilometers. And after doing that, we do a smaller one of 50 kilometers. The objective is to really look at the nucleus from various directions and characterize not only its gravity but also its shape. We have done, again, this is flight dynamics job, and our flight dynamics colleagues have already reconstructed with their tools the shape from a simulated one, and so we will have to construct modules in order to know exactly what we are flying around. Eventually, once we have detailed pictures, we will also identify landmarks. This is not a picture of the comet, it's a picture of the asteroid Lutetia, but more or less it gives the impression of what we're going to see at that time. We will identify landmarks and then calculate our trajectory corrections based on what we see with the pictures taken by the onboard camera about the surface of the comet. So we know how to direct the spacecraft. After that, we go into this detailed characterization of the surface. It means going closer. So from the top left, we come from the global mapping phase, which was the previous one. We go, from the early characterization phase, we go into the global mapping phase, and this is the type of orbits we're going to fly at distances of 30, 20 kilometers from the surface. That's the phase where we have to decide which place on the comet is the right place to land, and this is seen from another direction, and eventually, in November, it will be the time of depositing our lander onto the surface. You have to imagine landing here is not the landing that you can see in a Hollywood film or what you have seen also on landing on Mars or whatever. There's not so much energy involved. In fact, we have to do it very, very carefully. What will happen is that Rosetta will gently push away the lander from the body of the spacecraft, give it a separation delta V of a velocity of centimeters per second, and this will gently drop towards the comet. That's the separation orbit. This represents the separation orbit that we are planning. If you see the comet is rotating around this axis on the plane of the orbit. So if you land in the morning there, so you land at local 9 o'clock, it will rotate and it will be exposed to the sun for at least the initial phase of the mission. I should mention that from the models we have, we expect this rotation to last about 12 hours. So a day on the comet lasts about 12 hours. As I mentioned, landing is probably the most challenging operation we have to do, but that's only part of the mission. We have to stay around the comet also afterwards, and afterwards the game becomes even more complicated because the comet gets closer to the sun. When we are landing, it will be at about 450 million kilometers, it's 3 astronomical units. When it gets closer to the sun, the activity grows. I was a bit frightened to hear that the activity is expected to be already there when we arrive, but okay, I guess we can't change that. But there, it will get much, much higher. So activity that grows means more gas, more dust. We're talking about gas that flies away at 800 meters per second, so it's quite a speed. Of course, it's not very dense, but we have large solar arrays, very large solar arrays. So this shape is really not very ideal to fly in a dusty and very, very dynamically active environment. So that's going to be another challenge for Andrea's team. And this challenge will last for 1 year because we want to do this until the end of 2015. So flying around the comet there again, we had to forget flying around in circular or elliptical orbits, the nice orbits that we're used to fly satellites with. We had to learn how to fly, and we will have to learn how to fly. And at the moment, this is what we are studying. We're studying short flyby arcs. This is the way to get your spacecraft on the most stable possible trajectory. Eventually, this is what we're going to fly around, most likely. So it's going to be short arcs with steep corners that come back, and at the center of that shape, the comet nucleus will be. The distances will have to be adjusted to the activity of the comet and, of course, to the wishes of our scientists.